Hello and welcome to this project. We will start diving into data structures and you will see why object-oriented programming is essential to implement data structures in Python and in basically any programming language. First of all, what is a data structure? Let's see. According to the Merriam-Webster Dictionary online, a data structure is any of various methods or formats, such as an array, file, or record, for organizing data in a computer. The key part of this definition is organizing data. Those are the two key words in this definition. We use data structures to organize data. Just like you can organize shoes and shirts and socks in many different ways in your closet, and how you can organize, for example, books with different levels of complexity and sophistication, so you can find the ones that you read most often first, we can store data in data structures in very specific ways. So you can see why they are important. Let's dive deeper into this. Why are they important? The main goal of using a data structure is to organize the data efficiently and optimize common operations for a given scenario. For example, reading the content of the data structure, the values, adding data, removing data, and even updating data. Those are very common operations that we need to perform on the data that we store in a data structure. For now, let's say that these colored circles represent data. This data, at the moment, is not organized at all. You can see that they are just random colorful circles at any random position. But we can organize them in a linear way like this. Or perhaps like this. We can also use something similar to a tree shape. Or perhaps some data elements have to be connected to other elements in a specific way like this. Notice that in all of these diagrams, the elements are connected. And these connections are represented with arrows. This is essential in data structures, and you will see why in the coming videos. But these connections are like the glue of the data structure that keeps the elements connected. All data structures have certain advantages and disadvantages, particularly in terms of efficiency and speed for performing certain operations. For example, if we structure our data in a linear way, and we want to find this piece of data right here, the process could be slow if we can only start searching from the first element in the data structure, which would be this yellow circle right here. We would have to go from the yellow circle to the blue circle to the green circle and so on until we find this data that we are looking for. But if we change the order of the elements to have this tree-like shape and the connections look more like this, then perhaps we could read or retrieve the value much faster. So how can we choose the right data structure for our program? Well, we need to consider the pros and cons, or the advantages and disadvantages of each data structure, based on the problem that we need to solve. And based on that, we can choose which data structure optimizes the most common operations for our given scenario or problem. Great! After this brief introduction to data structures, you may ask, why is object-oriented programming important to implement data structures? Well, actually, object-oriented programming is sort of like their backbone. Metaphorically speaking, of course, but in reality, they are sort of like the backbone in code. Because with object-oriented programming, we can define the actual data structures themselves, create instances, define their elements, store their data, and represent their connections and implement their operations. That is amazing, right? In this project, we will see how you can do this with a detailed example of a particular data structure. We will implement all of its operations in Python. But first, here are some examples of different data structures and their names, so you can be more familiar with this area of computer science that covers data structures. First, we have arrays and lists. These are linear data structures that you commonly use. Arrays are typically used in Java, and lists are used in Python when we use square brackets. Then we have trees, and we have graphs. Graphs are amazing data structures that we use to represent connections between elements. So connections between cities or connections between warehouses or between members of a social network. And right here we have another data structure which will be the data structure that we will be working with during this section, linked lists. We will implement a linked list class during this project in Python. You will see that this is an amazing data structure. And this data structure will let us illustrate why object-oriented programming is essential to implement data structures in general. When you're ready, let's start working on the project. We will start with the node class in the next video. Welcome back. Let's start by talking a little bit about nodes and their role in data structures. Why are they so important? We will also implement a node class in Python. First, let's start with what they are. If we have certain values or data that we want to store in a data structure, in this case we have integers, and we want to make a data structure. How can we do that? Remember that data structures have connections. This is a key characteristic of data structures. Their elements are connected in a particular way. But we simply can't connect these elements directly. Why? They are just integers. They are values of a basic data type in Python. They are simply values. They do not have those special properties or capabilities of making a connection with other values or elements. What we can do is that we can take those values and we can surround them metaphorically with a capsule. A capsule made of code, and you will understand what this means in just a moment. But think of it as a capsule that provides additional functionality to the value, such as the ability of making connections to other capsules to form a data structure. These elements that I'm describing as capsules are called formally nodes. A node is a basic unit of a data structure, so you can think of them as the building blocks of data structures, a basic unit. These colorful circles that you can see right here and that you saw in the previous videos represented nodes. They didn't represent the actual data. They represented the nodes and their connections, because data structures are made of nodes that are connected to each other. A node can store two main elements: data, the value that we want to store in the data structure, and it can also make connections to other nodes. So these connections are stored in the node and kept as references. We will implement this in our code. We will have two attributes: the data of the node and the connections that it makes. This is essential for data structures because remember that their elements are connected. They are nodes and they have to be connected to other nodes so we can work with the data structure and perform the operations that we need to retrieve, read, update, and remove and insert data. We call these connections pointers. Formally. This is very important, this term, pointer. In this case, we say that the yellow node has a pointer to the blue node, because notice where this arrow is pointing to. It is pointing towards the blue node. So that means that we can reach the blue node from the yellow node. If we are in the yellow node, we can move through the data structure towards the blue node, but we can't go back because the arrow is pointing this way. We will see how this can be implemented in Python in just a moment using object-oriented programming. But first, let's define what a pointer is formally. A pointer is defined as a reference. Right here we have a reference to another node in the data structure. So basically each node is going to store references to the nodes that it is connected to. And that is how we are going to make those connections with our code. Great, let's look at the code and how you can implement the node class in Python. We will do this step by step, and we will also create some node instances so you can see how they work. Right here we have a new project in PyCharm. To create a new project, you go to File, New Project, and then you select the location of your project and you create a new environment. You can choose how to customize these settings. You can also use the default values. And then you click Create. Okay? In this case, I named the project Python OOP project. And I chose to start with a main file. This is where we will test our classes and our code. The main file will, by default, have some code right here, some sample code that you can just delete if you don't need it. In this case, we will not need it, so I deleted it. Let's start by right-clicking right here in the name of the project, and we click on New, and then Python file. We're going to create a new module. And this module will have the node class, so we write node. By convention, according to the Python style guide, module names should be written in all lowercase letters and separated by underscores if there is more than one word in the name. In this case, we just have the word node, so we write it in lowercase, and right there we have our new module, node. So we can start writing our class. First of all, we have to define the class using the class keyword, and then we write the name of the class, which is node. Remember that class names should always start with an uppercase letter. After that, we have to start defining the class constructor, the init method, like this. By default, PyCharm will add the self parameter, and after that, we need to define the two attributes of the node. What are those two attributes? In the video just a few moments ago, you learned that a node can store a value and a reference to another node. So those are the two values that we are going to assign in our class. You will see many variations of the node class. I'm just implementing a particular variation. As our second parameter, after we take the value, we can optionally take a reference to the next node, to the node that this node is going to point to. Remember that init is creating a node instance, so that instance can point to another node instance. We can take a reference to that instance, which is usually called next. You will usually see this reference as next, and we can assign a default value of none. So we make this parameter optional. If the user only wants to specify the value of the node, then he or she can only specify the value. The next reference is not necessary. By default, it will be none. But right here we see a warning that says that next, this name that we chose, shadows the built-in name next. And that is correct because in Python we have a function called next. And if we name this parameter next, we will not be able to use that function. You may choose to use this name, or you might like to adapt the name like this, next node. This is still readable, it's understandable, and it's concise, and it solves that problem of shadowing a built-in name. So we can just define our class like this. Now we have to assign the instance attributes. We say self.value is equal to value. And then we say self.next equal to next node, like this. Right here we can use the word next because we are not shadowing any names. This is just the name of an instance attribute. We're not shadowing any names. And it's not necessary to have the same word or the same name of this value and the attribute. We usually try to do that, but it's not strictly necessary. You could also remove the word node and shadow the name, but that can be problematic. So we just avoid this. And that is basically our node class. We have a value and a pointer to the next node. Remember that we are going to work with linked lists. In linked lists, each node points to the next node. So that is the only reference that we are going to take right here. We have the value and we have the pointer or the reference to the next node. Great! If that value, that reference is none, then the node doesn't have a next node. It is the last node in the list. Now let's see how you can expand this class to work with properties. You could also leave it like this because this is a very simple class. You could do that, but if you want to protect the data even further, you can just define these attributes like this and use properties. We are going to define the getter for the value. We use add property value, self is added by default, and we return the value of self underscore value. And there we go, we have our getter for the value. Add property, we define the property, this is the name of the property, value, self, and then we return the value of the instance attribute, which we had right here. Now let's say that we want to provide a setter for the value. We can do so with this syntax, add value.setter, and then we go to the value, and we replace the value. We need to add a second argument right here, which we are going to call new value. And that will be the new value for the node. We're just replacing the value attribute, the value of the attribute. And now we have our getter and our setter for the value attribute. In this case, it's already a property. We defined a property. So let's do the same with the pointer to the next node. Let's say that we want to provide that functionality. Next, with self, and we return self.next. Great, we have our getter, and we can also define a setter, depending on what you need and what you're trying to achieve with your node class. In this case, we have to replace the value of next, but we need to add an argument, like for example, new next, or new node, or new next node. You can assign any name you like that you think it's descriptive. So here we have a full node class with properties. This particular node is adapted to work with a linked list, to be part of a linked list, because we only have one reference or one pointer to the next node in the list. This node class will be very helpful when we start working with the linked list class. We're defining it on a separate module, so we can import it to our main file and work with it. If we save this file and we go to the main file, we can import this class, like you learned in the section where we covered import statements. We say from node, we want to import the node class. You will see that it turns gray because right now we're not using it. It says unused import statement. But we are going to use it in just a moment. We are going to define, let's say, node 1. In this case, you can also add an underscore right here to separate the number. And we see that we can access the node class. We can use the node class because we imported it from the node module that we have right here. We imported it so we can use the class to create an instance. We need to pass right here, let me zoom in, we need to pass the value that we want to assign to this node. Let's say that we want to assign the value 1. And we said that this next node parameter was going to be optional. That is why we don't have any errors when we only pass one argument. This value 1 corresponds to the value parameter. And this one right here, if we don't pass any value for it, it will just be none by default. So this node will not have a next node. It's just a node without any connections. So let's check that this node has the attributes that we defined. Let's check its value. We are assigning the value 1, so this should be the value of the node. If we run the code, we see this right here, the value 1. That is exactly what we expected. Now, if we change this value to 5, we should see it updated in the print statement. Right here we see 5, because now we are creating the node with the value 5. And if we check the next attribute, we should see exactly what we get right here, none. The default value was used, this default value for the parameter, because we didn't specify the next node in the sequence. This node doesn't point to any other nodes. Now let's say that we are creating a second node. This node will have the value 3, and we are going to make the first node point to the second node. We will have something like this, node 1 pointing to node 2. For that, we need to pass the second argument, which is next. This one right here, next node. We pass the reference to node 2, and we're saying that this node instance will have the value 5, and it will point to node 2, like this. So let's start analyzing how this changes our code. Let's check the value of node 1. It's 5 like we defined right here. And now if we check the value of node 2, it's 3 like we defined right here. So the values are being assigned correctly for both nodes. Now let's check the reference to the next node. Node 2 is the last node in the sequence that we're making right here with pointers. So the value of next for the node number 2 should be none, which is exactly what we see right here. This node, node 2, doesn't point to any other nodes. But now if we replace this with node 1, we see that it does point to a node object. This is the memory location where that object is stored. But right here we can confirm that this is a node object. So node 1 is pointing to node 2. We can check if that reference is node 2 like this. If the next pointer of node 1 is node 2, then we print that value and we see that it is true. So this reference, this object is equal to this object, is this object in memory. This node is pointing to this node like this. This is very important. It's very important that you experiment with this a little bit before you move on to the next video where we will start using nodes to implement the linked list. Awesome. So let's go through this class one more time to review all the small details. We defined the node class using the class keyword and the name of the class, followed by a colon and then a blank line. After this, we have the constructor, which is the init method. The self parameter is the first parameter, so we write that it is added automatically. And we use it to assign two instance attributes to the node instance, value and next. Value is the value of the node, the value that will be stored in the data structure. And right here, we are optionally taking a reference to the next node to create those connections. It is optional because we are also defining a default value for this parameter. If the user is not passing any value for this parameter, then none will be used. And that just serves as a way to indicate that the node doesn't point to any other nodes. It's just the last node in a sequence, or it's just an isolated node. It's just there, but it doesn't point to any other nodes. Right here, we are using the properties that you learned in a section during the course. So we can, for example, if we in the future want to check if the value meets a certain criteria, meets certain properties, then we can do that before assigning the value attribute with the setter. Instead of providing direct access to the value, we are using this intermediary setter method. And we're also defining a getter like this, like a property. So we can use the name value directly as an attribute. We're also doing the same for the next property, the instance attribute. We are defining a property with a getter for the next attribute, and then we are defining a setter for this property called next, where the user can pass a new next node, okay? Go through the class one more time yourself. Make sure that you understand all the details in the class and how you can import it to the main module. Like this, we say from node, from the node module. Notice that it is written in lowercase because this is the convention established by the Python style guide, writing module names all in lowercase. We import the node class, and we use it to create instances. We can pass the value, and we can also pass the value and the reference to the next node. So we can create this type of connection between the nodes. We will use these connections, and you will see how. This will definitely surprise you when we reach the part on linked lists. How we're going to use these connections to go from node 1 to node 2 and so on until we reach the particular spot that we need in the data structure. Great work so far. We've implemented the node class. When you're ready, go to the next lecture, where you will learn about linked lists and we will start implementing this class. Now you know how to implement the node class. So let's start learning about linked lists and why they are helpful. What is a linked list? A linked list is a linear collection of data elements. The keyword here is linear. This is a visual representation of a linked list. Notice that it makes a straight line where each element is connected to the next element. So that is why we call this a linear collection of data elements. Linked lists are made of nodes that are connected to each other through pointers. We can see this right here. Each element or node points to the next one. This is represented in this visual representation with these arrows that we have right here. And we will use this notation throughout the project. The connections make the sequence look more like a chain. And that is where the name linked list comes from. All the elements in the list are linked by pointers. Using pointers to connect the nodes is a characteristic of linked lists. Other data structures, like arrays, store the data in contiguous places in memory, so they can be referred to specifically using indices. This is a visual representation of those locations in memory. If you have these elements in an array, they will be stored in contiguous places in memory. Let's say that this is the computer's memory. But linked lists can store each node in non-contiguous locations, as you can see right here. And the pointers that we defined are used to get to the next node in the sequence, even if they are not physically next to each other in memory. So they can be very far apart in memory, and by the pointer, using that pointer or that reference, we can reach the next node in the sequence. Amazing, right? Well, these are two key elements of a linked list that you should know before we start implementing the class. The first one is called head, and the other one is called tail. What is head and what is tail? Head is the first node of a linked list. Like any list, a linked list has to start somewhere, right? So that is the first node. And it has to end somewhere as well. We are not going to have an infinite sequence of elements. The last node of a linked list is called the tail. This is the node that doesn't point to any other nodes in the list. There are two types of linked lists. Right here you can see a singly linked list, where each node points to the next node with only one connection in one way. You can only go from one node to the next. You can't go back to the previous node because there are no connections or pointers to go back. You can only go from the yellow node to the blue node, then to the green node, to the orange node, and so on. And if you want to start searching again, you have to start at the head again. The head, the first node in the list, will always be the entry point to the list. Some implementations also keep a reference to the tail of the list. And right here we can see another variation of the linked list, which is called a doubly linked list. It's doubly because it has two references. These references let the nodes point to each other, so you can go from one node to the next and back to the previous node, like in a two-way street. We will be working during this project with a singly linked list. And a nice challenge is to try implementing a doubly linked list yourself after completing this project. So if you want, you can try this as a challenge. Some of the advantages of linked lists include that the elements or nodes can be easily inserted and removed just by updating the pointers. They're also dynamic, so their length can increase or decrease as needed. They are not like arrays that have a fixed length and you have to create a new array when it's full. They are dynamic, so they can increase or decrease in size and length as needed. Now, they do take more memory than regular arrays. They take more memory because each node has to store a reference, so their backbone is taking more memory. Instead of actually just storing the values in memory, we're creating the nodes, and those nodes are storing additional references, so that makes them a little bit less efficient in terms of memory usage. Another disadvantage is that nodes must be read linearly, in the order that they are stored in the data structure, because we have to follow the sequence of pointers. We start at the head node, the first node in the list, and then we go through the sequence of pointers, we go through the chain, until we reach the node that we are looking for, or we reach the tail. We cannot jump from one node to the next to optimize the process. Based on these advantages and disadvantages, you can decide whether you should use this data structure for a particular purpose. So you need to decide based on these pros and cons. Awesome. Now think about how you would start implementing the linked list class in Python. Remember the attributes that we've mentioned. What are the two key elements in a data structure? In the next video, we will implement its attributes. When you're ready, start watching the next video and make sure to have your IDE ready, because we're going to code the linked list class. Welcome back. Let's start coding our linked list class. We right-click on the project and then we click on New and Python file. We're going to name the module linked list. The Python style guide recommends naming our modules in all lowercase letters and separating the words with an underscore to improve readability. So we're going to follow those guidelines. The first thing that we have to start writing in our file is the class definition. In this case, we're defining the linked list class. After we have that, we can start defining the constructor, which is the init method. We click enter right here and self is added automatically. In this case, for this particular implementation of the linked list class, we are not going to take any values as arguments when we create the linked list. We're just going to create a head attribute. This is one of the key attributes in a linked list, the head. Remember that we talked about the head and the tail. Well, there are certain implementations that keep a reference to the head node and to the tail node. In this project, we are going to keep a reference to the head node only, and we will use that as the starting point for all the different operations that we are going to implement. Initially, when we create a linked list, that head node will be the value none. So we assign by default the value none right here. Since this method is called when we create an instance of the class, the linked list will automatically have a head attribute, but that will initially be none because we don't have a head node until we insert our first node. Until that point, when we insert the first node, we have an empty linked list. Okay? And we also have to add this line right here. Why? Because we have to import the node class. We are going to work with nodes when we implement the different operations of this class, the methods, and we will start doing that in the next video. But for now, we write the import statement. Right now it is gray because we are not using it in the class, but we will use it in the next video when we start implementing the insertion operation. PyCharm also warns us that it expects 2 blank lines after the import statement. So we're going to follow that rule and add another blank line. Great, so now we have our class definition and initially the head of the list is equal to none. In the next video, we will start implementing the first method of this class, which will be inserting a node. When you're ready, let's start working on this first method, because inserting nodes is a key operation in any data structure. You have to insert data, update data, remove data, and also search for or find specific nodes. We will implement all of these operations in the coming videos. So when you're ready, let's continue. Let's write the necessary code for inserting data to the linked list. We will start by implementing how we can insert a node at the beginning of a linked list. If we have this node and we want to insert it to the data structure, we have 3 options based on criteria that we defined. We can either insert it at the beginning of the list, or we can insert it somewhere in the middle based on some sorting criteria, or we can insert it at the end as the new tail. In this video, we are going to insert the node as the head of the linked list. So we will be replacing the head, and this new node will be the very first node in our data structure. So the new node will be the new head. Like we can see right here. This is like a close-up to the data structure and how it will look like after we perform the insertion operation. This yellow node that we have right here was previously the head node. That is why we're calling it old head. And now we've included the red node before the yellow node in the list. We have the new head node and the old head node, which is now just a common node that is just part of the linked list. It doesn't have anything special. It's no longer the head node. The key thing right here is that we need to create the connection between the new head node and the old head node, so we can guarantee that we can continue having access to the linked list. That is what inserting the node at the beginning of the list is all about. We have to create a connection between the red node and the yellow node, so we can continue accessing the nodes sequentially. We will do this with our code through pointers. Think about how you would implement this in Python. Pause the video for a moment and then come back, and we will implement it step by step. Now we are back to our linked list class, and we have to start implementing the insert node method. The method is going to be named insert node. We take self as the first parameter, and then we have to take another parameter, which is going to be the value of the node. In this case, we are not going to ask the node itself. We are going to ask for the value as the argument, the value that we want to store in that node, and we are going to create the node in this method. You will see how in just a moment. We say new node, and we create the node from the value that was passed as the argument. We create the node instance. We can use the node class right here because remember that we are importing it from the node module. So we use it, we create the node right here, and we assign it to the variable new node. That is the node that we are going to insert. Now let's see what condition has to be true for us to insert the node as the new head at the beginning of the list. In the coming videos, we will complete this implementation for all the possible cases of insertion. Right now, we are just considering what happens if we have to insert the node as the new head. We say, if the head of the linked list is none, the Python style guide recommends using the is operator to check if a value is none or not, okay? So we use this operator. We should never use the equality operator to compare a value to none, according to the Python style guide. So we say, if the head is none, so if the linked list was empty, because that is what we have by default right here, when we just create the linked list and it's empty, the head will be equal to none. So we're checking if the linked list is empty. If that is the case, we just have to assign the new node as the head node. And that is what we are doing right here. I will scroll down right here, but remember that we have this import statement right here above, okay? We are assigning the new node as the head, because the list was empty. Now, we're going to implement our linked list in such a way that the elements are sorted in ascending order. This is a criteria that we are going to establish in this case, okay? So we can also say, elif the value of the head node if the first node, its value, is greater than or equal to the value that we are going to insert, then we have to insert the new node as the head node. So what are we going to do? We are going to change the pointers, like this. The new node is going to point to the head node, to what used to be the head node. At this point, it's still the head node, so we are reassigning the pointers. We're taking the first node, and we're saying the new node will point to the first node in the list. And after that, we just replace the head node with the new node. The new node is now the head, and the head is now just another node in the middle of the list. Take a moment to pause the video and analyze this code and really understand how we are reassigning the pointers and the logic of the code. This condition is also equivalent to this right here. If the value is less than or equal to the value of the head node, then we do this. I think this can be more helpful to visualize what is going to happen. If the value that we're trying to insert is less than the value of the head node, then we have to assign the node as the first node in the list because we're trying to preserve the order of the values in increasing order. So We take the new node and we make that new node point to the head node. And now, after we have that, the new node is the first node in the list, and we replace the head of the linked list. And those are the two possible cases that we could find to insert a node at the beginning of the list. If the list was empty, so if the head node was none, then we assign the new node as the new head. And if the value of the new node is less than the value of the head, then we just add it as the new head. Okay? Take a moment to pause the video, analyze this, and then come back because we are going to test how this method works and we're going to create an instance of a linked list. Okay, right here we have some code in the main module where we created some node instances and we tested our code, but we're not going to use this right now. We're going to replace the code and now we are going to import the linked list class from the linked list module. And what are we going to do with this class? Well, we are going to create a linked list and we're going to name it my linked list. We're going to use the class to create an instance of the linked list. Okay? We know that to create the instance of linked list, we don't need to pass any arguments. The head will be none by default. We can check this with a print statement, my linked list.head, and we run the code and we see the value none, because the head is by default none. Since the head is equal to none, any nodes that we insert will be the new head. Okay? Because this will be true, the head is equal to none, so we assign the new node as the head. So we can try this method right now. My linked list, and we call the method insert node. And what value do we assign to the node? Well, anything we want. In this case, we're going to work with integers and numeric values because we're trying to preserve increasing order. That is why we're making this comparison right here. We're going to keep the list in increasing order. That is not necessary. It depends on how you want to sort the data. We're just implementing the data structure this way. Let's assign the value 9. After we call this method, the data structure will have the value 9. And we can check this by printing the head node. Okay? Like this. If we just print the head node, we will see that it has a node object. It is a node object. It's no longer none. But how can we actually check that it is the node that we inserted? Well, we can check if its value is equal to 9 by using dot notation again. With this, we are referring to the head node of the linked list. And then, by using another dot and value, we are getting the value of the head node. We run the file and we see the value 9, which is the value of the node that we just inserted. Awesome, right? Now we can insert nodes. Now let's try another value to see what happens when this part of the conditional is executed. If the value that we're trying to insert is less than the value of the current head, then we have to replace the head and reassign the pointers like this. Let's insert, after we insert the value 9, let's insert a value that is smaller than 9. Let's insert the value 3. According to what we've implemented, we should have this sequence after these two calls to insert node are executed. We should have a node with the value 9, which used to be the head node, and after we insert the node with the value 3, this should be the new head node. We had 9, and after that we are inserting the new head. So if we print the value of the head node, after this we should get the value 3. Let's run the code and see what we get. That is precisely what we get, the value 3. Awesome, right? So we've implemented two main parts of the insert operation. Inserting at the beginning if the list is empty, and inserting at the beginning if the value should be there, if it's the smallest value in the list. Now in the coming video, we will be implementing the case where we have to insert the node somewhere in the middle of the list, preserving the increasing order. Okay? When you're ready, after you review all the details of the code that we wrote during this video, go to the next video to start implementing and completing the code for this method. Great work so far. Now let's see how you can insert a node in the middle of a linked list. If we want to insert a new node, this new node, at this particular location in the linked list between the green and the orange node, the first thing that we have to do is to remove the connection between the green node, which is called the previous node, and the orange node, which is called the runner node. We will use this notation, and this is very common when we work with data structures, previous and runner. You will see why this is called runner in just a moment, but it is related to the fact that it will change. Right here we have the new node. Instead of having this connection, we are going to create a connection or a pointer from the green node to the new node. And then we're going to create a pointer from the new node to the orange node, the runner. If we zoom in to see this part of the list after we've made those changes to the pointers, we will see that this results in the linear structure made with pointers. That is just a continuation of the linked list. So we're getting the same structure with the new node in the middle. We said previously that we always start moving through the linked list from the head node, which is the first node. So how can we find the insertion spot, or the place where we need to insert the node, based on the values? We will need to define certain criteria to sort the nodes if we want to insert a node in the middle. In this case, since we are working with integers and the nodes contain integers, we will be working with increasing order. So we will know that if the node reaches a point where all the values are greater than that number, then that is the insertion spot. Basically, we start at the head node as the previous node, and the next node is the runner node. We check right there if the new node meets the criteria for inserting the new node at that point. If it does, then we insert it there. But if it doesn't, we need to keep searching. And how do we do that? We move the previous and the runner nodes to the right. We're not actually changing anything in the data structure. Instead of being the yellow and the blue nodes, now they are the blue and the green nodes. You will see how we do this in our code. If this is the right place for inserting the node, then we insert it right there. But if it doesn't, we keep checking, and we keep updating the previous and the runner nodes. Once we find the right location where that node meets the criteria, for example in our case, that would be if this node has a value that is greater than this node, and this node has a value that is less than this node. Okay? So if this is less than this node, and this is greater than this node, we know that this is the insertion spot to preserve increasing order. We insert it just like you just learned. We make a pointer from the green node to the red node, and then from the red node to the orange node, from the previous to the new node, and from the new node to the runner. Think about how you would implement this in Python. Pause the video for a moment and then come back. I promise you that this will be very interesting, because we're working with new concepts, previous and runner, and you will see how they are updated. Make sure that you understand the basic principles of how this works, and if you need to, go through the videos as many times as you need to. These concepts have many details, and it is important to go through them many times to understand how they are implemented in the code. When you're ready, let's start working on the code. Now let's see how we can implement this in our code. We're going to continue working with the insert node method. Remember that in the previous video, we only covered the cases where the nodes had to be inserted as the new head. Okay? Now we're going to implement what happens if we have to search for the insertion spot and insert the node somewhere in the middle, like you saw in the diagrams. For that, we are going to use an else clause right here. We say if none of these conditions are true, so we don't have to insert the node as the head node, we have to start searching. And how are we going to do that? Well, we are going to define two variables that you saw in the diagrams. You saw these names, previous, which is going to be the head initially, and runner, which is going to be the node that is next to the head, the node that the head points to. That will be our runner. Why do we have to use this peculiar syntax? Well, because we only have the reference to the head. That is the only thing that we keep or store for the linked list, the head. So we have to work with that. We start from the head and then we get the next node from the head. Those are the values of previous and runner. We're just assigning new names to these nodes, to this pair of nodes that we can use in our code. After that, we have to write a while loop. We have to use a while loop because we don't know how many iterations we will need to find the insertion spot. What are we checking? First, we're going to check if the value of runner is not none, okay? If we haven't reached the end of the list, because the runner will be none at some point when we reach the end of the list. Well, this is not the case and we haven't reached the end of the list, then we need to continue searching. If that is the case and the value that we want to insert is greater than the value of the runner, okay? So if the value of the node that we want to insert is greater than the value of the node that we're currently evaluating, the runner, then we have to move forward and continue to the right. We haven't found the insertion spot yet because the value is greater than this value. We have to continue moving to the right to preserve increasing order. How do we do this? How do we move forward or move to the right? We moved previous and runner to the right as a pair, okay? We updated them both at once. So that is what we are going to do. What used to be the runner is now going to be the previous node because we are moving them to the right. And now the runner will be the node that came after the previous runner. The runner is now going to be the previous node. We moved one node to the right. And now, what used to be the next node of the runner will be the runner. We're moving one node to the right. Until this condition is false, we will continue moving to the right. When this is false, then we've either found the insertion spot or we've reached the end of the list. So, what we do is we reassign the pointers. The new node will point to the runner because, as you saw in the diagram, right here, the new node is always in the middle between the previous and the runner node. So the new node has to point to the runner node and the previous node has to point to the new node. That is how we make the pointers to create the linear structure that keeps all the properties of the linked list. Awesome, right? With this code, we can insert a node, preserving increasing order in the data structure. Let's review what we have right here. In these first two conditions, we check if the node has to be the new head node. If that is not the case, then we go to the else clause. And what are we going to do? We are going to define two variables, previous and runner. Previous is going to refer to the head node initially, and runner is going to refer to the second node in the linked list, the node that comes after the head node. That is why we use the next pointer. We are getting the node that is after the head node. While we haven't reached the end of the list, so the runner node, which is the node to the right, is not none, and the value that we want to insert is greater than the value of the current node, then we just continue moving to the right by reassigning the values of previous and runner. What used to be the runner now will be the previous node, because we moved one place or one spot to the right. And what used to be the node that came after the runner will now be the runner. We're just moving to the right in the list. Once we reach the insertion spot or the end of the list, because this condition is false, then we just reassign these pointers. The new node will point to the runner, and the previous node will point to the new node. Okay? That is exactly what you saw in the diagram. Great, so now we've implemented insert node and we can test it. If we go to our main module, previously we saw that if we used insert node like this, we would have this linked list. The node 3 would be the head, and then the node 9 would be another node after we insert the head, the new head, which is 3. Let's see what happens if we insert a value that is in the middle of these two values. Let's say 6. Insert node 6. Okay. We're going to insert 9. After that, we're going to insert 3, and then we are going to insert 6. What's going to happen first? We're going to have a linked list with a node, with just one node, which will be the head with 9, the value 9. Then we're going to insert the value 3, and that will make a linked list with two nodes, 3 and 9. The node with the value 3 will point to the node with the value 9. And then, after we have those values, we are going to insert the value 6. And how are we going to do that? We are going to insert the node in the middle between these two values. We will have a node with the value 3 that points to a node with the value 6, and that node will point to the node with the value 9. 3 will be the head and 9 will be the tail. This will be the final state of our linked list when we print its values right here. How can we check if this node is successfully inserted? Well, we can see its value. We can check its value. If we have a reference to the head of the linked list, that will be 3, the node that contains the value 3. But we can use next to get to this node, which is the node with the value 6. And if we print that value, we can use parentheses right here so you can see this a little bit better. First, we access the head node, and then we access the next node, and then we access the value of that node. But these are just redundant parentheses. We can use dot notation like this, without parentheses. We get a reference to the head of the linked list, then we use that to get to the next node, which is the node with the value 6, and we print the value. Okay? That is basically what we're doing right here. Let's save the file and run our code. And we see exactly that. We see the value 6, which is exactly what we expected. Now let's see what value we have for our head node. Right here, if we remove .next, we will just get the value of the head node, like this, which is 3. That is correct, and that is what we expected. Now, we can go even further and reach the third node, like this. From the head node, we reach the next node, which is the node with the value 6, and then we reach the next node from that node, which is the node with the value 9. And we print its value so we can check that it is correct, and that is what we expected, which is the value 9. So the structure of our linked list is currently what we expected, 3, 6, and 9. Awesome, right? Now we can insert elements at the beginning of the list and at any particular point in the list or spot to preserve increasing order. Preserving increasing order is just something that I decided to do in this implementation of the linked list. You don't necessarily have to do that, but you have to decide a specific criteria for sorting the elements if you want to be able to insert the nodes in the middle of the linked list. Great work so far. Go through this code one more time, at least one more time, and make sure that you understand how this part of the code works. I would recommend reviewing the code with the diagrams from this video, so you can relate what is happening with the visual representation. Great work so far. When you're ready, go to the next lecture, where we will see what happens if we try to insert a node at the end of the linked list as the new tail. I will see you there. Now let's see what happens if we try to insert a node as the new tail. That means, in our case, in our implementation, that the value is the largest or greatest value that we have inserted to the linked list so far. And how can we do that? How can we reach the tail to add the new node as the new tail? Well, we start from the head, like we always do. The head is always our starting point for these operations. Then we use the pointers to reach the next node and the next node and the next node until we reach the tail. Once we reach the tail, if we have like a close-up right here, we can see that we have to add the new node to the tail. This is a graphical representation of what we are going to do with our code. We sort of place the new node right after the tail, and we have to create a new connection between these nodes so we can reach the new node from the old tail. We create that connection through a pointer, and we have what we call the old tail and the new tail. This is no longer a tail. It's just a regular node, another node in the middle of the list, and this new node becomes the tail. So this is the only one that we can refer to the tail after we make the insertion. The only thing that we have to do is to create a pointer or a connection between the old tail and the new tail. Okay? Think about how you could implement this in your code. Pause the video for a moment and then come back. Great work so far. We will see this in our code. Right here, if we go back to our linked list class and we go back to our insert node method, we will see that our code already covers that case, this part of the code, the else clause. Why? Because we are working with the concepts of previous and runner. And we can take our previous and runner nodes as far as the tail. We can reach the tail and we can insert that new node as the tail. Okay? We will continue as long as the runner is not none, and while the value that we are trying to insert is greater than the value of the runner. Let me show you how this works to insert a node as a new tail. Let's go to our main module. We have right here the state of our linked list after these 3 lines, and now we are going to write a 4th line where we are going to insert a new node. That will be the new tail. So far we haven't replaced the value 9 as the tail. Well, in this case, there was just one node. But so far, in these 2 steps, the value 9 has always been the tail. Now let's try to insert the node 15 to see how it works. 4th. After we run the 4th method call, we are going to have a linked list that looks like this. 3, 6, 9, and 15. These are all nodes that contain these values, okay? So if we save the file and run our code, but first we have to update this right here. We are going from the head, which is the node with the value 3. We're going to the next node, the node with the value 6, then to the next node, the node with the value 9, and we still have to go to another node because we have 4 nodes now. We have to use next 3 times to reach the node with the value 15, and then we're going to print that value. We're going to use this line to confirm that the 4th node in the linked list is now 15. Let's save the file and run the code, and effectively we see the value 15 printed as the output right here. That is exactly what we expected. So now we have 4 nodes. With this, we can confirm that. We're using head, then we are going to the 2nd node, to the 3rd node, and then to the 4th node. And we're getting the value of the 4th node. And that is returning the value 15. So that is awesome. Our code already handles that case where we need to insert the node as the new tail. Great. So we have our insert node method already implemented to cover all possible cases, inserting as the head, inserting in the middle, and inserting as the new tail. Make sure that you understand how this code works before you move on, because we will be using the concepts of previous and runner in the coming operations that we will implement as new methods. Great work so far. When you're ready, start watching the next lecture, where we will start traversing a linked list so we can print all its elements. Welcome back. Now we're going to implement a method that will traverse a linked list so we can print all its values. First, let's see what traversing means. According to Merriam-Webster Online, to traverse means to go or travel across or over. And that is essential because in the world of computer science, which we often abbreviate as CS, traversing means visiting every element in the data structure and doing something with the data of each one of those elements. In this case, we will print their values, so we will write a print list method. How do we traverse a linked list? Remember that we defined a head node for the linked list. We will use that head node as the starting node for the entire set of operations that we will implement. We used it to insert a node, and now we will use it to traverse the list. We start at the head, and then we print its value. Then we use the node's pointer to move to the next node. Then we print its value. Again, we use the blue node's pointer to move to the green node. Then we print its value, and we repeat the process until we reach the tail, which is the last node in the list. We also print its value, and then we stop. The traversal has been completed. We accessed or visited all the elements in the data structure, all the nodes, and we did something with their data, which is printing the values in this case. We could do anything we wanted with that data, but that is the basic principle of a traversal: accessing the values, all the values, and doing something with the data. In this case, this method will be very helpful because we will be able to see with just one method call the content of the entire data structure. Think about how you would implement this in Python. Pause the video for a moment and then come back. We will implement it together. So when you're ready, come back and we start to code. Great, we're back to our linked list class in PyCharm. We have our insert node method, and now we are going to start implementing a new method to traverse the list. This method will be called print list items. You can assign the name that you find most descriptive. For example, print elements, print nodes, print values, anything you like. In this case, I named it print list items. How are we going to implement this method? First of all, we need to check if the list is empty. How are we going to print a list that is empty? Well, we have to choose what we want to print. How do we check if it's empty first? Well, we check if the head node is none. If the head node is none, then there isn't a head node and the list is empty. In that case, I decided to print empty right here. You can print another message or you can handle this scenario as you like. But if that is not the case, then we have to start using the concept of a runner. In this case, we're not going to use the concept of previous. We're only going to use the concept of a runner, because this will be the node that we will be updating as we move through the list to access each one of the nodes. We don't need to update a pair of nodes. We just need to keep track of one node, and that node will be runner. I'm calling this runner. In some implementations, you may see this as the current node. Okay? Initially, we're starting from the head. So we are using the reference to the head node, self.head. And we are assigning that reference to the runner. After that, since we don't know when we are going to reach the tail, we have to use a while loop. And we say, while the runner is not none, so while we haven't reached the end of the list, this will include the tail node because the tail node is not none. This will only stop when we pass the tail node. While this happens, then what are we going to do with each one of those nodes? We are going to print their values. So we are going to print the runner's value on the same line, separated by a space. Let me explain this. When we use a print statement, we usually see the output printed on different lines, but we can change this with the end parameter. Since we want to present the list as a sequence of values, the values of the nodes, on the same line, we need to pass this parameter, the end parameter, and we specify a space. So we want to separate the values with a space and print them all on the same line. That is what we are going to do right here. After that, we just have to update the runner. And what are we going to assign as the next runner? The node that came after the current runner. We're taking the current runner, the current node where we are at, and then we are finding the next node in the sequence, and we are assigning that next node as the new runner. That is how we get that effect of moving through the list towards the right, going node by node and checking its value. I recommend using this print statement right here because we want to separate the output of this method from the output that we generate from other methods or other method calls, okay? If we don't add this print statement, then the next output will also be printed on the same line as these values, and that is not what we want. We usually want to get the output separated with one line per method call. So this is very helpful. Great, so now we've implemented this method. Let's go through its details one more time and then we will check how it works. We have the print list items method. This method will print all the elements or the values of the nodes in the linked list on the same line in a sequence. We define this method with the self parameter and then we check. If the head is none, so if the list is empty, then we just print the message empty. But if it's not empty, then we have to start moving through the list. We start from the head and we assign the head to the variable runner so we can update it. And we say while the runner node, which is also called the current node, is not none, so while we are iterating over the nodes in the list, we print the value of the current node, and then we update the value, the current node, to the next node in the sequence, in the list. And that is basically how the code works. We add this print statement for presentation purposes, so the next output will be on a separate line. Awesome. Let's save the file and go to our main file so we can test this right here. Now we can use our method instead of using this sequence of next attributes. We can just use this. We replace this and we say my linked list dot print list items. We use empty parentheses because this method doesn't take any arguments, only self, and self is not included when we call a method. What we should see is this sequence of values printed as the output, 3, 6, 9, and 15, because we've inserted these values like this previously. Let's save the file and run the code. And that is exactly what we see right here. We see the sequence of values 3, 6, 9, and 15, and we also see the value none. Why do we see none? Because we are printing the value returned by this method call. Since we are not returning any values from the method call, we are just printing the values, we get the value none. So this can be solved by removing this call to print. We run the code and we just see the sequence of values as the output. That is exactly what we expected. This is the structure of our linked list after we inserted these nodes. So we see these values in the same order as the output, separated by a space. Awesome, right? Great work so far. Now let's see what happens. For a moment, let's comment out these method calls, and let's see what happens if we print the list items of an empty list. Let's say that these insertions never happened. So the linked list is still empty at this point. If we print the items, we see the message empty. So the method also handles that case if the list is empty, if the linked list is empty. Awesome, great work so far. Make sure that you understand the details of this implementation. We're checking if the head is none to check if the list is empty, and if it's not empty, then we are just running through the sequence of nodes, printing their values, and then getting the next node in the sequence. That is basically the logic of this method. When you're ready, start watching the next lecture where we will implement a method that will count the number of nodes in the linked list. I will see you there. Another important operation that we should implement as a method in the linked list class is to count nodes, to note how many nodes are in the linked list at any given moment. To implement this, as always, we start at the head node. And in this case, we start with a count of 0. Before we've added the head node to the count, we increment the count by 1 because we're in the head node, so there is at least one node. Then we reach the blue node and we increment the count by 1. Then we reach the green node and we increment the count by 1. Then the orange node, the blue node, and finally we reach the tail. You can see how we are updating the count. At this point, we update the count to 6 because we were in the tail and we stop. So we return the final count from the method. There are two ways to implement this: iteratively, using loops, and recursively, calling the method recursively. I will show you both ways to implement this, and this will be a great opportunity to work with recursive methods. These are just like recursive functions, methods that call themselves. Think about how you would implement this in your code. You have to traverse the list and keep a counter to know how many nodes you have visited so far. Pause the video for a moment, try to come up with a solution, and then come back so we can start writing the code. Welcome back. Right here, we're with the linked list class in PyCharm. Let's start implementing count nodes. Okay, you can also name this getCount. I like the name count nodes. I think it's very descriptive. Okay, so this particular method, for the iterative implementation, we are not going to take any arguments. We want to count the nodes from the head to the tail, inclusive. What do we need? We need a variable to keep track of the counter, how many nodes we've visited so far. So we are going to define the variable count. After that, we have to get a reference to the first node that we are going to visit, and that will be the head node. We'll be updating this to move through the list. And we say, while, we use a while loop because we don't know how many nodes will be in the linked list. And we say, while runner is not none, then what do we have to do? When we go from one node to the next, we have to increment the count because we visited one additional node, and we also need to get a reference to the next node so we can analyze or visit the next node in the linked list. And that is what we are doing right here. We are getting the next node that comes after the runner node, and we are assigning that as the new runner. So we're visiting all the nodes and incrementing the count for each one of the nodes that we visit. After we complete that loop, when we reach the tail, we just return the count. In this case, we are going to return a value from this method, the value of the count. Why does this condition work? Well, while the runner is not none, then that means that the node is a valid node. It is not the value none. The tail is also a valid node. It is not the value none. So this will work correctly, and it will return the value of count. This is the iterative implementation using a loop. Let's see how it works if we go to our main script. Right here, we had 4 calls to the insert node method for the linked list. And we said that the state of the linked list was this. We had 4 nodes with the values 3, 6, 9, and 15. Now, instead of printing the items, we want to count the nodes, okay? And for that, we just need to call the new method that we defined right here, count nodes. We take the list, the instance of the linked list, and we count how many nodes it has. But first, we have to print this value, okay? Why? Because instead of printing the value right here, we are returning the value. So it's not going to be printed automatically as the output. We have to print it ourselves. If we save the file and we run the code, we see the value 4, which is exactly what we needed. This value is correct. We have 4 nodes in this linked list, 3, 6, 9, and 15. These values are all part of their own individual nodes. Okay, now let's see what happens if we insert another value, like my linked list, insert node, let's say the value 0. And then again, we print the count. Let's see if it is updated correctly. It is, because first we see 4 right here on this line, and then when we insert another node, we see the count being updated to the value 5. Now let's see what happens if we print the count of nodes of an empty linked list. Let's say that we didn't insert these values. We will just comment them out momentarily until we test what happens. We just have the linked list, and this linked list is empty right here because these are comments at the moment. We are not inserting any values. We see the value 0, which is the correct value. The method is providing the expected output. If the linked list is empty, then the value will be 0. There are no nodes in the list. Great, this was the iterative implementation using a loop. Make sure that you understand the details of this implementation before moving on, because now we will start to dive into the recursive implementation of this method. You can implement them both ways, okay? They're exactly the same, but usually iterative implementations are a little bit more efficient in terms of performance because they do not generate all the different calls in memory, and the while loop is usually more efficient. But you can do it both ways. Let me show you. We will delete this implementation of the method, and we will say count nodes. And right now, since this is a recursive function, we will have to take another argument, which we will name node, okay? And we say, if the node is none, so if the node is no longer a valid node and we've reached the end of the list, then we return 0, okay? That is our base case for the implementation of the recursive function. Now, else, what is our recursive case? A recursive case would be to add 1 if the node is valid. If this is false, then the node is valid. We go here and we add 1. And to that value 1, we add the result of counting. We have to use self.count nodes, starting from the next node in the sequence, okay? How are we reducing the list? We are passing the next node as the argument, and that is how we are getting the count. If the node is none, then we reach the end of the list and we are going to add 0 and stop the recursive process. Else, if we haven't reached the end of the list, we are going to increment the count by 1 and we are going to add the result returned by calling the method recursively with the next node as the argument. Okay? This is how the recursive implementation works. The iterative implementation that you just saw is equivalent and it works exactly the same. This is just to show you that the same operation can be implemented in different ways. And this is also illustrating how we can have recursive methods. Methods that call themselves. Notice that we have to use self right here because we are calling a method from the instance, okay? Let's save the file and go to our main program. Right here, our main module. Now we see sort of a warning right here where we see count nodes. Previously, we didn't take any arguments, but now we do have to take one argument, which is the initial node, the node from which we are going to start counting. In that case, since we want to start counting from the head, we will have to specify that we want to start counting from the head of the linked list, okay? We pass that as the argument, myLinkedList.head, to the method countNodes. If we save the file and we run the code, we see 4 as the output. And that is correct. We had 4 nodes and we see the value 4 as the total count. So our recursive method works correctly. But this aspect, this characteristic of having to pass an argument to the method is not very practical because usually we want to start counting directly from the head. It really makes no sense to specify the head as the argument. Let's delete this and change our implementation of the method to make life easier for the users of our method. Instead of having to pass an argument that should be assumed by default, we are going to create something called a wrapper. We are going to define a method like this, count nodes, that is going to call this method. So right here we are going to change the name to count nodes recursive. We can also abbreviate this as rec or recursive. I think this is more descriptive. We have the same method right here. But what we are going to do now, and we have to update this right here, because we are calling the method recursively, so these should have the same name, okay? In the new method, countNodes, which is the method that the user is going to call, we are going to execute or call countNodesRecursive, passing self.head as the argument. Okay? And that is basically how we can implement this to make life easier for the user of our method. Instead of calling this directly, the user will call count nodes. And count nodes will call this method, already specifying that we want to start from the head of the linked list. This is an example of how you can change the internal implementation of a class without changing how the user interacts with your code. If we go to our main file, now we see that we don't have any warnings. The user can still use the method as it did when we had the iterative implementation. We didn't change anything of how the user interacts with the method. The user doesn't have to pass any additional arguments. He or she can just call the method using empty parentheses, and the program will work correctly. We changed the internal implementation and not the interface. But we still have a small detail right here that we need to implement before we can actually call the method. And that is adding a return statement right here. Why? Because this method will return the count, but this is the method that we are calling. So we have to return that value instead of just calling this method. We have to return the value returned by the method. Okay? We are calling this method indirectly, but this method returns a value. It returns it right here. But before, we were not returning the value from this method, so the user will not receive the value. Let's test this. Right now, like we're implementing this right here, we don't have a return statement in this method. So if we call the method, we will see the value none, because the method count nodes is not returning any values. We don't have a return statement right here, and there should be one. So we just write return right here, and that way we will be returning the value that results from this method call. Now, if we save the file and run our code, we see the value 4, which is exactly what we needed, because we have 4 nodes in the linked list. Awesome, right? You learned 2 different implementations of the count nodes method, an iterative implementation and a recursive implementation. And you also learned how you can change the implementation of a method without changing how the user interacts with the method. And that is essential, because imagine if you try to make some changes to your code and that would break everywhere in the program where you use that method. Great work so far. When you're ready, let's start working on the next lecture, where we will implement a method to find a node in a linked list, so we can verify if a particular value is in a linked list or not. When you're ready, let's start working on it. Welcome back. Determining if a particular value is in a linked list or not is another very important operation. We call this finding a node. In our implementation, we will return true if the value is in the linked list and false otherwise. Let's say that we want to find this orange node in our linked list. We can see the list right here visually, and we know that it's in the list. But in practice, you will not know if the node is in the list, and you will need to call a particular method to check this. Like always, we start searching at the head node, and we ask, is this the target node? No, it isn't, so we use the pointer to reach the next node in the linked list. And we ask the same question. Is this the target node? No, it isn't, so we use the pointer again to reach the next node, the green node. We ask, is this the target? Since it isn't, we go through the pointer again, and now we ask, is this the target node? Well, this certainly looks promising. We check that, and it is. We found it. So we return true to the method call, to the place where we called that particular method. In this case, we found the item in the linked list. But if we had been searching for an item that was not in the list, then we would have reached the tail. We would have continued our search, and once we have confirmed that there wasn't a match, we would have returned false to the method call. You can start thinking about how you would implement this in Python, in the linked list class. Pause the video and then come back so we can implement it together. We only have 2 main operations left. So when you're ready, let's get started. Right here we are again with our linked list class. We only have 2 main operations left to implement during the project, so great work so far. Right now, we are going to implement the findNode method to determine if a node is in the linked list or not. We go to the end of the file after the last method defined in the class, and we start defining this new method, findNode. As always, the method takes self as the first parameter, and we also need to take right here an argument because we want to get the target value. We need to know what node we are searching for, what value we are trying to get, okay? We can name this target value, target, value, anything you like. I'm just assigning this name to make the code more descriptive. How are we going to start finding or searching for the node? We need a runner node. We need to go and move through the linked list using a reference to the nodes, but we are going to start from the head as usual. After that, we have to use a while loop because we cannot know in advance how many times we have to move to another node. And we say while runner is not none, then we check. What are we going to check? Well, we are working with valid nodes in the list and we haven't reached the end of the list. We are going to check if the value of the current node is equal to the target value. If that is the case, then we found the node and we return true. Else, if that is not the case and the current node is not the target value, then we need to update the runner to point to the next node so we can continue moving forward. That is the basic logic of these 3 lines of code. If the value of the current node, which we are calling runner, is equal to the target value, then we return true. But if it's not, then we just need to move forward and we assign the next node as the runner node. Else, if the while loop is completed and there wasn't a match in any of the nodes in the list, then we return the value false. You can use some spaces right here to make the code more readable, like this. So we find the node by using the target value. We start from the head, which we are calling runner. In some implementations, you will see this mentioned as the current node as well. In this case, I'm keeping the concept of previous and runner, so we can be more consistent. And we say, well, runner is not none, so while we are searching through a valid part of the list and we haven't reached the end, if the value of the current node is equal to the target value, then we found the node, we found a match, and we return true. But if that is not the case, and this condition is false, then we just need to update the runner to runner.next. We could also write an else clause right here to be more explicit in our code. We say else runner equals runner.next. The else clause in this case can be omitted because we have a return statement right here. If this is true, then the value true will be returned and the execution of the method will be stopped. If this is true, then the method will stop automatically after the value is returned. So this line will never run. It's basically like having the else clause right here. It's the same effect, okay? But if you think that this is more readable visually, we could also use this. I am going to keep this like this. Else, if we haven't returned the value true during our search, that means that we haven't found a match, and we return the value false at the end of the method. Great, so now we have our implementation of findNode. Make sure that you understand all the small details that are happening right here to make the process work correctly, from the argument to the loop and to the return statements. Make sure that you understand their role and why they make the process work correctly. Now let's test this method findNode in our main script, in our main file. We have a linked list and we inserted these values. So this is the final state, the current state of the linked list at this point. Previously we were counting the nodes, but now we are going to find a node in the list, in the linked list. We know that we've inserted the values 3, 6, 9, and 15. So let's check if the value 3, the head, is in the linked list. We run the code and we see the value true. And that is correct because 3 is in the linked list. Now let's test a node that is in the middle of the list, like the node with the value 9. Right here we see true because it is part of the linked list. We can also check the tail, 15, and we also see true. But now if we try to search for a node that doesn't exist in the list, like for example 27, we will see the value false. The node is not in the list. If we try with a value that is smaller or less than the head, like 1, we also see false. And if we try with an intermediate value that is not in the list, like 5, we also see false. So this works correctly. Now what happens if we have an empty linked list? How does the method work in that case? Let's comment these lines of code so we can see what happens. In this case, we are not inserting any elements. We just have this empty list and we call the findNode method with a value that is not in the list. We see the value false, which is correct. The list is empty, so 5 cannot possibly be there as the value of a node. Okay, awesome work. We only have one major operation left, but before you get to that video, make sure that you understand how this method works. Making diagrams and adding comments to your nodes can be very helpful to understand the concepts of previous and runner and the value and the head. There are many concepts involved in these operations, so reviewing them and explaining them in your own words can be very helpful. When you're ready, let's start working on the final operation that we will implement, delete node. Welcome back! Great work so far! We almost reached the end of this project, and we only have to implement the delete operation. We've implemented a fully functional linked list class, and you can say that you know how to implement a data structure using object-oriented programming. That's awesome, right? Well, let's start talking about the final operation that we will implement in our class, which is deleting a node. Let's see how we can delete a node from the beginning of the list. We will break this operation into 3 steps or phases, just like we implemented the insertion operation in 3 different stages. This is the node that we want to delete. Let's say that we want to delete this node. It's yellow. In this case, in this example of a linked list, it is the head node. If we zoom in to this part of the linked list, we can see this part of the data structure in more detail. We want to remove this node, the head node. And for that, we need to use the pointer to reach the blue node. We will start at the head, and then we will use the pointer to reach the blue node. Why are we doing that? Let's see. This blue node will have to be the new head, because we are removing what used to be the head. The linked list has to have a head, the first node that we are going to use to reach or get to all the other nodes in the sequence. So we need to assign this node, the blue node, as the new head node. And that will automatically detach the old head node from the data structure. Remember that we use the head node, which is an attribute of the linked list, to reach the other nodes in the sequence in the linked list. If the head node is updated, then the old head node is no longer accessible by the data structure. The data structure has no access to this node, which is exactly what we needed. And that is how we remove a node from the beginning of a linked list. Now we can start the operations from the blue node instead of the yellow node. This is what the data structure will look like after we remove the yellow node. Now the head is the blue node. Think about how you can implement this in your class. Remember that you have to assign the next node as the new head node, the second node in the linked list. Pause the video, analyze this for a moment, see if you can implement this in your code, and then come back. Here we have our linked list class. Now we have more methods implemented, and we have to implement one more, delete node. Let's go to the end of the class, and let's add this new method. Let's define it. Delete node. As always, the first parameter is self, and then we have to know what we want to delete. So that would be the target value. We're going to take the value. The first thing that we have to check in our method is if the list is empty. We can't delete something from an empty data structure, so we check if the head is none. If it is, then the list is empty, and we return false. Usually, we return a Boolean value from this method to indicate if the deletion operation was successful or not. In this case, it wasn't successful, so we return false. This is in the case where the list is empty. But if it's not empty, we still might need to delete the head node. So let's implement that case. If the value of the head node is equal to the target value, what do we have to do? We have to get the next node, the second node in the list, and assign that as the new head node. And that will automatically sort of detach the head node from the data structure, the old head node. Now the second node, the node that comes after the head node, will be the new head. And then we return true, because the deletion operation was successful. This is really nice, right? We can delete the node from the head if it matches the target value by just assigning the second node as the head node. Okay, so now we have these two cases implemented. We will have a third case in case we need to delete the node from the middle or from the end of the list, of the linked list. But we will implement that in the coming video. For now, let's test how this method works with our main module. Let's uncomment these insertions, so we are going to insert the data, and we have our linked list. This is the final state of our linked list with these 4 nodes. And what are we going to do? Instead of finding the node, which we had right here, we are going to delete a node. What node are we going to delete? Well, right now we only implemented the case where the list is empty, which is not, and where we delete the head node. So we want to delete the value 3, the node with the value 3. To confirm if the node was deleted successfully or not, we are going to call the method printListItems. Okay? We're going to print the state of the linked list before we make the deletion and after we make the deletion. We can also remove the spaces. Let's save the file and run our code. We see as our first output the state of the linked list that we have right here. 3, 6, 9, and 15. We have all those 4 values printed in the same sequence that we expected. And right here we see the value true, because the node 3 was deleted successfully, the node with the value 3. And after that deletion occurs, we see the new state of the linked list, 6, 9, and 15. The head of the linked list was removed. So this works correctly. Now let's see what happens if the linked list is empty. Okay? Let's comment this out so we are not inserting anything. These are just comments for the moment. And we have our linked list, which will be empty. We print the list items, we try to delete a node, and then we print them again. Let's see what we get. We get the correct output. We see empty because the linked list was empty at this point. Then we see false because the deletion was not successful, because we have an empty linked list, we have nothing to delete. And then we print it again and we see empty. So the program works as we expected. Great work! We have these 2 cases implemented. When you're ready and you understand how this works in detail, make sure that you understand how this is reassigning the head node. We will go to the other cases where we need to delete the node from the middle and from the end of the list. Great work so far. Now let's start the second step or stage or phase of this implementation, where we will implement deleting a node from the middle of the linked list. If we want to delete this green node, for example, we can see that this is somewhere in the middle of the linked list. So let's see how we are going to do that. Our target is this green node. We start at the head node. As always, we always start the operations at the head node. And right here, we are going to use the concepts of previous and runner, like we did before. And we have the 2 concepts in the same operation. We update these nodes continuously until we reach the node that we want to remove. Until the runner node is the node that we want to remove, our target node. In this case, our target node is the green node that we want to delete. Remember that the runner node, this one right here, has to be our target node, not the previous node. Once we get there, we need to remove the connections between the other nodes that surround that node, the previous node and the next node of this green node that we want to delete. And we remove these connections by changing the pointers in such a way that we sort of make a bridge between these two nodes, the previous node and the next node, the blue node and the orange node, as you can see right here. Now this sort of bridge will make the blue node point to the orange node directly. So we are kind of isolating poor green node. So this list will no longer have access to the node, and it's like it doesn't even exist. So we deleted it successfully. Since linked lists work with pointers, if there isn't any pointer to that node, it's like it doesn't exist. And that is what we are obtaining or getting by making this sort of bridge with the pointers. The final data structure would look like this, where the green node is no longer accessible and it's no longer part of the list. Think about how you would implement this particular part of the operation. Pause the video, think about the details of how you would reassign the pointers to make that bridge, and then come back. We will work on the code step by step. We are back to the linked list class, and if we go all the way to the bottom, we will find our delete node method. So far, we've implemented how to delete a node when the linked list is empty or when we have to delete the head node. But now let's implement how to delete a node from the middle of the list. We saw in the diagrams that now we have to use the two concepts, the concepts that we learned previously of previous and runner. So let's do that. We start by defining previous, which is the head node, initially. Remember that we use these variables to move through the linked list. So initially, previous is head and runner is the second node. Head.next. Once we have those initial references, we can start checking if we reach the end of the list and if the nodes are still valid. Let's see. While the runner is not none, so we haven't reached the end of the list, and the target value that we want to delete, the value of the node that we want to delete, is greater than the value of the current node, the value of the runner, then we need to continue moving. And how do we do this? We do this like in the other operations. The runner is now the previous node, and the new runner is the node that came after the runner. We're moving all the references to the right, so we can move forward in the linked list. And after we do that, after we found the actual node that we want to delete, that is the runner, when the runner is the node that we want to delete, then this condition will be false. Okay? And we say, if the runner is not none, like this, we can use parentheses to make this more readable. So if the runner is not none, then we haven't reached the end of the list, and the value of the runner is equal to the target value, then we found the node that we want to delete. In this case, in this implementation, we are not assuming that the list has the target value. So we check if the value of the runner node is equal to the target value, then what are we going to do? We are going to reassign the pointers in such a way that the previous node points to the node that comes after the runner. This is a little bit tricky to understand, but think of this as the bridge. We are making a connection that skips the current node, the node that we want to delete. We had previous and we had runner. Runner is the node that we want to delete. So what are we doing? We're making that arrow that forms the bridge between previous and the node that comes after the runner. Previous will now point to the node that comes after the runner. That is basically what this line means. Previous will now point to the node that comes after the runner node. The runner node is the node that we want to delete. So this is basically making the bridge that we need to isolate that node. In that case, we made the deletion appropriately, so we return true. But if that is not the case, then we didn't find the node in the list, so we return false. The deletion was not successful because the node was not found in the linked list. Great! So if we remove these comments right here, we have our final implementation of the method. We are checking all the cases. We are checking if the list is empty, we're checking if we have to remove the head node, and we're also checking if we have to remove an elementary node somewhere in the middle of the list. Great, awesome, so let's save the file and go to our main script, our main module. If we uncomment this to insert these values, we can start calling the method. Let's do this. This is the structure, the current structure of our linked list. We have the values 3, 6, 9, and 15. If we want to remove a node or delete a node, let's say that we want to delete the node 9, okay? So the final linked list would be 3, 6, and 15 with their corresponding nodes. We can check that this works correctly by printing the list items first and then printing the list items after we make the deletion. We can also print the value returned by delete node, so we can know if the deletion was successful or not, true or false. Let's save the file and run our code to see how it works. Awesome! This worked exactly like we expected. We had a sequence with the numbers 3, 6, 9, and 15, which were the nodes in the linked list. And the deletion was successful because we got the value true. And after we made the deletion, we deleted the node with the value 9. So we only see these three values, 3, 6, and 15. The deletion was successful. That is awesome. Let's test this with different nodes, like for example deleting the head node, which is 3. This worked correctly as well. And now let's try deleting the node with the value 6. It was removed successfully, so our code is working like we expected. Now let's see what happens if we try to delete a value that is not in the linked list, like 27. Right here we see that the value false is returned because the deletion was not successful. The linked list is not affected. We see the same 4 values in the sequence. Great, now our linked list can delete nodes from the middle of the list. I really suggest analyzing the details of this implementation. Make diagrams and write your own comments on each one of these lines of code to make sure that you understand how the process is working. Great work so far. Now we've implemented all the main functions. In the next video, we will see what happens if we try to delete a node from the end of the linked list. And that will be our final video for this project. Welcome back. Finally, we have to consider how we can delete a node from the end of the linked list. If this is the node that we want to delete, we see that it is at the very end of the data structure. It is the tail. So we will need to use the concepts of previous and runner again. We will update them as we move through the linked list until we reach the tail. We need to break the connection between the previous node and the runner node, which is now the tail node. We do this by removing the pointer from this blue node to the green node that we have right here as a tail node. That way, the green node is no longer accessible by the linked list, and the blue node becomes the new tail node because we have sort of detached the green node right here. From the data structure, we no longer have a pointer to this node. Think about this for a moment. How would you implement this operation using the concepts of previous and runner? What determines if a node is a tail node or not? Pause the video for a moment, think about this, and then come back. Right here we have our linked list class. And if you think about this carefully, we actually don't have to make any changes to our code. In our delete node method, right here in our else clause, we are already taking into account what happens if the runner node, the target that we want to delete, is the tail node, because we are checking if the runner is not none. This will get to the tail node if needed, because the last node in the list is still not none. We will continue moving through the list until we potentially reach the tail node. And if we find a match, like this one, we will just make the bridge. In this case, the code will still work because we will be assigning a null pointer to the last node in the list, and that will completely detach the last node, what used to be the tail, the old tail. Let's see this in our main file. Let's see how this works. We are inserting these values, and let's say that we want to delete the node with the value 15, which is the tail right here. We are printing the items before we make the deletion, and then we are printing the items again. We see this as the output. The program works correctly. We had our sequence of 4 values, and then we see the value true because the node was successfully deleted. And after that, we see the linked list without the final value, 15. That is awesome. The code that we wrote in our last coding session works for this case as well. If the node that we want to delete, the target value, the node with the target value, is the tail node in the linked list. So we had 2 per 1. We were deleting in the middle of the list, and we were also considering the case where the node could be the tail node. This is great! So congratulations, we've implemented a fully functional linked list class. With the attribute head, using the node class to insert a node, and checking where we have to insert the node, then we can print all the list items, we can count the nodes iteratively and recursively if you want to implement it like this. We can also find a node and know if it's in the list or not by returning true or false. We can delete a node from the start, from the middle, and from the end of the list. So we have all the major operations of a linked list class implemented using object-oriented programming. You should be very proud of yourself. Think about how much you've learned since you started the course. Now you know how to implement a data structure using object-oriented programming. This is a very common question during interviews, and these principles will help you understand how other data structures work, so you can implement them yourself in your code using Python. Great work!